This is going to be a simple video on alkenes. I'm going to be talking about what is an alkene, what is the structure of an alkene, what is the properties, how do we name them, and I think I'm going to save how we make them in a separate video. So what is an alkene? An alkene is going to be a double bond between two carbons. So in this case, we have ethene, where there's a double bond between this carbon and this carbon. This would be an example of an alkene. If we take a look at this carbon here, and I count how many bonds it is, or how many atoms it is attached to, there's 1, 2, 3. This tells me that this is an sp2 hybridization, which tells me the structure is trigonoplanar. And I can see that if I draw out the sp2 orbitals. So there's an sp2 orbital here, there's an sp2 orbital here, there's an sp2 orbital here. Now, because it is an sp2 hybridization, this carbon also has a p orbital. So I'm going to do the same thing for the other carbon. And the p orbital. So this overlap right here, this overlap right here between the two carbon orbitals, that is a sigma bond. But now, because we have the two p orbitals, we have a pi bond. So alkenes have a pi bond and a sigma bond. Because of this structure going on, the locked-in p orbitals kind of make it harder for our alkenes to rotate, like how our alkanes would rotate. So there's not going to be a lot of free rotation happening for alkenes in room temperature. In order for you to rotate this molecule, you'll have to break the pi bonds, but we'll kind of get into that. I think just not now. Okay, so some of its properties, I'm going to be talking specifically about melting point and boiling point and stability. So for melting point, let's take a look at, let's say, propane versus propene. They're going to have very similar melting points and boiling points. So, in other words, alkenes are going to have very similar melting points and boiling points as their corresponding alkanes. So, for example, these would be they would have approximately equal melting points and boiling points. However, if you compared maybe this molecule with this molecule, now this is butene, and so is this. This is also butene. But the only difference is that this is in a trans configuration. So this is trans butene, and this is a cis configuration. This is what we call stereochemistry, which is how the molecule is actually shaped, or the bonds are all in the same place, but it's just the shape of the molecule that it's in. So if it's cis, we're going to use Z to show that it is cis, and E for trans. So when we compare these two, a cis and a trans molecule of the same alkene, the trans one is going to have a greater melting point. And that's because the trans configuration is much more stable. So it's going to require more heat to melt it. Versus cis, because of these substituents that are on the same side of the double bond here, they don't like being in that position. It's too much sterics, or in other words, too much strain. The hydrogens here on this carbon, the hydrogens here on this carbon, they're going to want to repel. So this is a more favorable configuration, and that's why it would have a greater melting point. I just talked about how a trans configuration is more stable than a cis configuration. Another way to identify whether an alkene is stable or not very stable is through hyperconjugation, and basically all that means is if it's more substituted, it is more stable. So what do I mean by that? We can have ethene where there's no substituent, there's nothing added onto the 2 carbons here. It's not going to be as stable. Oh my goodness, what is that? What the heck? It's not going to be as stable as, let's say, that's propene, which now has one substituent on the double bond. But let's add another one, which will be this molecule, where there's 2 alkenes on the same, or 2 substituents on the same carbon, which we can kind of have different ways to add 2 substituents. Remember, we can also do this. We can get the cis configuration, or we can do the trans configuration. Now, let's make it stronger. All we have to do is add another substituent. Now we have 3 substituents, and of course that's not as strong as if we had 4 substituents. And this is going to be our most stable when there's 4 substituents on the carbons, and it's going to be very substituted. Versus this one doesn't have any substituents, so it's going to be very stable than this compared to this one. Okay, so now I want to talk about nomenclature. How do you name it? First, I want you to remember the suffix "ene." Now, if you know how to name alkanes, this is going to be very easy for you. Remember, this is ethane. If I add a double bond, this becomes ethene. And if I have propane, I add a double bond, this becomes propene. And so on and so on. But once you get to butene, you can have a butene with a double bond here, and you can have a butene with a double bond here, or you can have a butene that looks like this. These are all butene. So how do you name them to be able to differentiate between all of them? Let's start off with, I'm going to try to space this out. I'm going to start off with the left one. This one, I see that it's in a trans configuration. So I have to denote that it is trans, which is E. And I see that the double bond is on the first carbon. So it's E1 butene. So if you look at the second one, it is also in a trans configuration. But the double bond is on the second carbon. So I put 2 butene. And the last one is in a cis configuration. That is Z. It's on the second. The double bond's on the second carbon, so it's 2 butene. So this is how you would differentiate between different molecules that are the same ene, but they have different, whether the double bond's on a different position or whether it has a different stereochemistry. Okay. So this one on the left, let me look at the double bond. There is substituents on the same side, which tells me that this is a cis configuration, which I would denote as Z. Now I'm going to count the number of carbons. There's 1, 2, 3, 4, 5, 6, 7, which tells me that it's heptene. Now I have to specify where the double bond is. So I can either have it on 1, 2, 3, 4, or I can have it on 3. I want it on the smaller number, so I'm going to go according to the blue numbering. So it's going to be Z3 heptene. This one on the right, this one's a little tricky. You can see that the methyl groups are on opposite sides, and these bigger substituents are also on opposite sides. This tells me that it's a trans configuration, which is E. Let me count the longest carbon chain. This would be 1, 2, 3, 4, 5, which is pentene. Oh, there's substituents. Okay, I gotta be careful. Let's move this towards the end. Let's see where the pentene is. 1, 2, or 1, 2, 3. 2 is a smaller number, which is 2. Now let me actually write it out. 1, 2, 4, 5. And I should see that there's a methyl on 3, and there's a bromo on 2. I'm just gonna write 2 bromo. Oh no, I'm out of space. Okay, goodness gracious. 2 bromo, 3 methyl, 2 pentene would be the name of this molecule. Oh my goodness. Oh my goodness. Okay. There we go. This would be the name for this molecule here. That was torturous a little bit. I'm sorry for doing that to you. I guess the one thing I want you to take away from this is if you look at the two different substituents, this one's bromo, this one's an ethyl, they're on opposite ends. So this should tell you that it's trans, and that's the main thing I wanted you to take away from this problem. Not that I wanted to torture you with this long-ass name. Okay. Awesome. So the second suffix I want you to remember is going to be ennyl. You're going to use this suffix when the alkene, the double bond, is not a part of the longest chain. So, let's do this one. I'm going to locate the longest chain, which is this one. 1, 2, 3, 4, 5, 6, 7, 8. This is octane. And my substituent is on the 1, 2, 3, 4, or 1, 2, 3, 4, 5. 4 is a smaller number. I'm gonna number it left to right. It's on the 4th carbon of the octane. So I see that our substituent here has 1, 2, 3 carbons. This is gonna be prop. And because our alkene here is not a part of the longest chain, we use the suffix ennyl. So it's going to be propenyl octane. But I have to specify where the double bond is within my propenyl. I can see that it is on the 2nd carbon. So I have to put propen 2-eel octane. 4 propen 2-eel octane would be the name of this molecule. So I want you to try to name, let's do this molecule. Pause the video and I'll give you the answer like right now. Okay, so my longest chain is of course going to be the cyclohexane here. So I just put that as my base. Cyclohexane. And because there's only one substituent, I'm just going to assume that it's on the carbon 1. So I don't have to specify 1 cyclohexane. So, yeah. I see here that there is 1, 2, 3. It's going to be propenyl again. But I don't have to specify where the alkene is either because it's on the first substituent, so I can just write propenyl. But I do have to specify that it is in a trans configuration, so it's going to be E. E-propenyl cyclohexane would be the answer to this problem. The last suffix I want you to remember is going to be, bear with me here, illidine. You use this when one carbon of the alkene is a part of the main chain while the other carbon isn't. It's gonna look something like, let's do that. It's gonna look something like this. So to name this, I'm gonna locate the longest chain, which is 1, 2, 3, 4, 5. So it's gonna be pentane. This is either on the 1, 2, 3, 4th carbon or the 1, 2. I'm gonna choose the smaller number, so 2. Count the number of carbons, 1, 2. So it's gonna be is it ethanilidine? I'm pretty sure, yeah, ethanilidine pentane would be the answer to this one. All right. So I want you to try. Let's just do a simple one. Something like that. Yeah, you know what? Do that. Okay. So it's gonna be, I'm gonna count the number of carbons. 1, 2, 3, 4, 5, 6 is hexane. This is either on the 1, 2, 3 or 1, 2, 3, 4. 3 is a smaller number. So it's going to be 3. And there is 1 carbon. So it's meth. And because only half of the one is a part of the longest chain, I'm going to use the illidine ending. So it's 3-methylidine hexane. Last thing I want you to remember or note is if there is an alcohol present, so let's say something like this, the alcohol is going to take precedence. It's more prioritized. So I'm going to name it, if there is a, I'm going to name it according to the alcohol. So I'm going to start by numbering the carbons starting from closest to the alcohol. So it's going to be this way and not this way, because we want to prioritize the alcohol. So I don't want this numbering system, I want that one. So here, I'm gonna have 1 ol, that's the ending for an alcohol, so ol. There's a 1, 2, 3, 4, 5, so it's pent. Theta bond is on the 4th. Pentene 1 ol would be the name of this. Just note that if there is an alcohol, it will take precedence. It's more prioritized. You're going to name it according to the alcohol and not the alkene. The alkene would be considered a substituent. Okay, and I think that's the end of the video.